All right. I think we've set things up to stream. Yeah, we're getting close to the main goal for this little crash course in Rham theory, which is to help set things up to stream. Yeah, we're getting, namely to let physicists sort of start to learn this language of Rham theory, which is a natural one to understand topics such as the Whitehead integral for Hopf invariant. We're getting pretty close. Today, we're going to talk about pullback, homotopy invariance, degree, and linking number. So this gets very much topological. So we've talked about forms as stuff to integrate, and now we're going to sort of shift perspective gradually and understand what those integrals measure topologically. So the first thing I want to talk about is something called functorality, which means basically how you can move things around, how things behave well with respect to continuous functions. So the starting point is actually in the negative, that vector fields are not functorial for smooth maps. So you can imagine having a vector field on some surface. I'm going to sort of it does all sorts of crazy things. And if I'm mapping one surface to another, and often a perfectly good function is like a projection onto the XY plane, we've used those kinds of things. Well, then if I take a point in the XY plane and I look at a couple places over it, you will notice that there's two different vectors at the point above the pre-image. So if I'm trying to send my vector field through a function, you get a sort of a type mismatch, because a vector field, I really need one vector at every point. And because more than one point can go to the same place, I mean, this could much worse. This could all send the whole original surface to a single point in the second surface. That would just be a constant function. So it's not, it's not that interesting, but it's a perfectly good case to consider. But there's no vector field. There would be no information away from that point, and the information would be almost certainly highly contradictory at that point. But forms are functorial. Namely, if omega is a form on some manifold and I've got a map between those manifolds, then the pullback of omega, well, it's got to be something that eats a bunch of vectors. And how's it going to do that? Well, I can send vectors one by one from the domain to the range. That's often called the Jacobian or the derivative. And that includes for the map that I just wrote below. And lo and behold, if I just do that, it's easy to check that that I get some set of vectors in the range, and I can apply the form. So so it seems a little bit odd. So vector fields are not functorial, but this is really local. So, and above, when we have more than one vector mapped to the same point, what would happen when we're evaluating a form above is we would call the form at that point, in this case twice. Once it would, if I had some curve, let me draw that in. Suppose I had a curve that happened to go through these 2 points, and it was tangent. I didn't draw that well, tangent to those vectors or whatever. And I wanted to integrate a one form over that curve. Well, I would use the one form at this point on two occasions. right, in this definition. And it just works out. I don't have to, each occasion it's using the vector once. First time it'll be using that vector, and second time it'll be using that vector. And the one form has no problem in just sort of using that once at a time. And so it's kind of tricky, but it sort of solves this basic problem. I mean, sort of functorality is this Jedi power for pure mathematicians. And we like to have it when it's natural. We often call it naturality, by the way. And it allows for things like changing coordinates and again, sort of understanding, moving around a calculation until its meaning becomes clear, all sorts of great things. So let me give you an example related to things that we've been doing previously, and just to also, yeah. So what I want to do is first, let's go back to the circle. And there, of course, you know, if I look at the circle within this plane, I've got x squared plus y squared equals 1. One little trick is that if I differentiate this, I get 2x dx plus 2y dy equals 0. So I can look at forms like dx and dy on the circle, and they're sort of dependent, not linearly dependent, but they're dependent everywhere. There's really just one form, and on the circle that that's the basis for everything, and that's our d theta that we talked about last time. But dx and dy exists, and d theta on the circle, by the way, you know, let's sort of rederive the formula for d theta. If I'm at my point xy, then the tangent vector is going to be minus yx, and then the form is dotting with the tangent vector, and so that means that our d theta on the circle is minus y dx plus x dy. And we've talked about d theta before, and if you looked at that formula and you just realize that on the circle x squared plus y squared is 1, this agrees. But let's then give another derivation. Let's try to extend it to all of our 2. So use this pullback notion. So consider f from R2 minus the origin to this circle. That's going to send, I'm going to use 2 different sets of coordinates, uv to u over u squared plus v squared to the 1/2, v over u squared plus v squared to the 1/2. So uv, point in the plane, projects onto, if I'm anywhere here and I've got my unit circle, uv goes to this xy. So I've got that projection from R2 minus the origin to the circle, and let's calculate the pullback. What we're going to do is basically say, well, if x is u over u squared plus v squared to the 1/2, then dx is going to be u times 1/2 times u squared plus v squared to the minus 1/2 times the derivative of the inside, which is by the chain rule 2u du plus 2v dv. I'm just taking the total differential, and if I've got some variable, I take the derivative of the function in question, and then I'm going to multiply it. It's d of my zero form becoming a one form is all that's we're following. So that's numerator times the derivative denominator. Then I've got my denominator. Times the derivative of my numerator. That's easier, right? And then I'm going to divide by the denominator squared. And let's then say that let's skip right to, if that's dx, then y dx is what? It's v times u squared plus v squared to the 1/2 times, well, now, times this. And that's going to be, after a little simplification, v times u squared plus v squared times u du plus v dv minus v du over u squared plus v squared. Phew. And so the claim is that then x dy is going to look similar, but with the roles of u and v reversed. And you notice that most of this is symmetric. Everything except the minus v du is symmetric. So you deduce that x dy minus y dx is going to be v du minus u dv over u squared plus v squared. So that's a bit of calculation, and that's how pullback goes. It's really just the chain rule, changes of coordinates. It really did, that's what this d Jacobian is just taking the derivative, but then when you pull back, you're using the definition of d of a form to apply that chain rule, so to speak. Okay, so that's an example I wanted to give. So functorality helps us establish invariance. Right, let me just say this is equal to the pullback of x dy minus y dx. And really, there wasn't an equality here. I mean, there is sort of an equality in how they work, but these two forms are living in different places. X dy minus y dx was living on the circle. The u dv minus v du minus u dv over u squared plus v squared is living on all of R2. Okay. So functorality will help us establish invariance. So I'm going to make a definition that is non-standard. If I have a manifold, I'm just going to call it good for short. If it is compact, so it doesn't go out to infinity or have any points missing. If it has a boundary, the full boundary is there. Oriented, so no Klein bottles or Mobius strips. Connected, so just one piece. Let's just say with no boundary. So that's what I'm going to mean by a good manifold. Usually, for some reason, we haven't we don't have a good single word for this kind of thing. So I'm just using the word good. And suppose we have a map from M to N where M is good, N is arbitrary, and omega a closed form on N. So that means that d omega is 0, its derivative is 0. So think like a locally constant function, but again, the remarkable thing is that in this higher dimensional geometric setting, you get a lot more solutions to the differential equation dx df or whatever d omega is 0 than you do on Euclidean space. So and so then what we can do, we consider the number where we pull back the closed form and integrate it over the domain. All right. And then the theorem is that if F is homotopic to G, so you can get one map to the other through some one parameter set of deformations, then these numbers are going to agree. All right. So, I mean, so the picture is I've got maybe some one form and it's counting some sort of winding number around the two holes, maybe some linear combination of hole things. And if I've got two different maps from a circle, maybe one winds around like this, and the other, which is similar but might look fairly different, can have a lot of wiggles, and there's a deformation between them, I know that those integrals are going to be the same. Okay. So let's give you a quick proof. It's going to come down to Stokes's theorem. So homotopic means that there exists an H from M cross the interval 0, 1 to N, so that H restricted to time 0 is F, and H restricted to time 1 is G. Then we take the integral over M cross I of D of this H upper star omega. So we can still pull back to now M cross I, integrated over M cross I. Well, some further functorality says that this is going to be the pullback of d omega. That's another functorality property. I didn't even bother, but pullback commutes with external differential. But d omega was assumed to be 0. And then by Stokes' theorem, this is the same as the integral over the boundary of M cross I of just the pullback of omega. But the boundary of M cross I, M has no boundary, it's good. And so there's only the two endpoints. And so this is the integral over M cross 0 of H restricted to 0, pullback omega. Minus on the other side, the orientation gets reversed, M cross 1, H restricted to 1, pullback omega. And that is just what we're looking at, integral of F upper star omega M minus the integral of G upper star omega M. And we're saying that that's 0, so those two numbers are equal. So it really just comes down to the star of our show, one of the main stars of our show, which is Stokes' theorem. The generalized Stokes' theorem is fundamental to so many arguments in differential forms. Okay. Similarly, Suppose if omega equals d tau, then the integral over m of f upper star omega will be zero itself. And let me leave the proof as an exercise. It's going to look a heck of a lot like what we just did. Great. So in light of this, so we can call closed forms on N the Rham cohomology invariance of, well, we've talked about maps to N, but you could really just think of it as an invariant of in itself. And then the kernel of the differential, those are our closed forms, modulo the image of the differential. Those are the ones we just considered in the previous theorem. Those we can ignore, their integral, they'll give zero invariance. These two vector spaces sit inside the image of the previous D sits inside the kernel of the next, because D composed with D is zero. And that's often sort of thought of as a equality of mixed partials kind of equality. And this is going to be the in degree K, the kth de Rham cohomology of N. All right. So so K forms give some kind of invariance of a manifold that gives another meaning. It gives an invariance of maps into the manifold. So let me give you, and calculating this de Rham cohomology is often fairly interesting. It's still kind of, there's plenty of interesting manifolds, in particular if you look at configurations of points within some ambient manifold. You're studying some sort of fields or particle theory within some kind of space or space-time. We have lots and lots that we don't know. It's one of my main research interests, is those spaces we call them configuration spaces, different from physicists' configuration spaces. Okay, let me give you the most probably important calculation of this. And unlike the previous theorems, this one's much harder. I'm not going to go into the proof. So if N itself is good, then, and it's say dimension D, then this de Rham cohomology in degree D is a rank 1 vector space. It's just R, and the isomorphism is given by sending some form. It's going to be closed, by the way, because if N is dimension D, there are no D+1 forms. There's no way to take D+1 vectors on N and have a good sense of D+1 dimensional volume, because they're all going to be linearly dependent. They're going to be degenerate. So any D form is closed. And what we're going to do is just integrate over N, and we'll get a number. And that's the isomorphism. So we call these not at least the ones that don't go to zero under this sort of volume forms, or especially if the ones with total volume 1, we often call volume forms in particular. And what this is saying is, that if two forms have the same integral, they're going to differ by something which has an antiderivative. Okay. So that might make sense, like on R, right? If you've got, or on a circle is a good example. on a circle, of course, one form, I can just think about the function because it's function times d theta. I could have this, which is a volume one form versus this, which is a volume one form. One is very uniform across the circle, one is very concentrated. And the difference would be have total volume zero. And what you could do is just take the antiderivative of that difference as I go along the circle, and that would be something whose derivative is what we want. But that's just a first very easy case. In general, this theorem is hard. It's one of the things that we take a fair amount of time to prove in a graduate algebraic topology class that does de Rham theory. There's other approaches to cohomology for sure. De Rham theory is actually not covered in those cases, and it's maybe people learn it elsewhere. So this is part of something called, it's sort of a first case, key case of Poincare duality. Okay, but let's take this hard theorem and apply it. Because now what we're going to do, M and N are going to be good of the same dimension. Then what we're going to do is say the degree of some map from M to N is going to be the integral over M of the pullback of omega for any omega with total integral 1 over N. So take my favorite volume 1 form and pull it back, and that's going to be the degree. So when you define something like this with this choice for any omega, so then the theorem, you have to pretty quickly, hopefully, prove that this is independent of choice and an integer. Okay, so the independent of choice, I'll again leave as an exercise to using the couple theorems that we just cited. But let me get to the integer part. So first, let me give a proposition about any point in N. There is a form omega, which is a D form, so that the support of omega, where it can return some non-zero value for to some set of tangent vectors on N, because by the way, the zero form is always a form. It's always available. Just, hey, you ship me some tangent vectors. I'm always going to say N. I'm always going to say zero. So the support is where anything interesting can happen. The support is going to be contained in some ball around P of radius epsilon. That's also something we can choose. The integral over N omega is going to be, of course, then the integral over this ball of omega, and that's, we're going to call it 1. And we're going to call this the tome form at P. And so that just has to, I can take a, say, a multi-dimensional Gaussian with, although Gaussians go to infinity, so I might want to do like an e to the minus one over whatever, e to the minus one over x in order to get something that cuts off. You do it in Euclidean space first, and then you use the fact that any manifold has these Euclidean neighborhoods to say, okay, this exists. So just conceptually, I've got my n, I've got my point. N can be very complicated, very twisted, but I choose a small enough epsilon, and then there's going to be some basically function that has integral one supported there. And then I can just, it's that function times, the top dimensional, like d theta on the circle or dx wedge dy wedge dz on R3. It's just going to be that function times that top dimensional form. You could also think of it as a Dirac form. Okay, so then to prove the theorem, we're going to use this as our volume form. To prove that degree is an integer. What we do is you have your map from M to N. We assume that for all y, so that map to this P, f of y equals P, we're going to have df at y is non-singular. So just df is if you use local coordinates, it's a matrix, it'll be invertible. Its determinant will be not zero. And then what happens is, I've got my P, and that's in N. Well, in M, I have all these different Y's that that map to P. I'm going to choose my epsilon for my bump form so that these go to nice disjoint balls. And then my integral of f upper star of this tome form is just going to be a sum of plus or minus one at each point in the yi, so that f of yi equals p. I'm going to just take my form here is this highly concentrated form which integrates to one. It pulls back to a highly concentrated form at each point that integrates to plus or minus one if the map sort of did some sort of orientation reversing, which is pretty common. Like if I've got a sheet folding over, the two pre-images of a point will have opposite orientations, and so I would get plus one and minus one in this kind of calculation. But the point is that is an integer. Okay. And in fact, so that's the proof. But in fact, the proof leads to this definition of this alternate, sort of more basic, if you will, definition of degree. And so let's go through some examples. So if I've got M and N both a circle, I can think of maps between the circle that sort of map one to the other by winding around a few times. It could even reverse, but the total number of times I wind around is going to be the same as degree. Same, very similar on the unit sphere. if I'm thinking of this, the complex numbers with a point at infinity, and for example, I take z to the n, this will have degree n, or in fact, any polynomial. This is part of the naming of it, any polynomial of degree n will have degree n. And there's a proof of the fundamental theorem of algebra that sort of relies on this. What's another one? If any map from S2 to itself, or any M to M, misses a point, in other words, it maps to S2 minus any P, well, I could use that P as my point in the domain that I'm pulling back around, and it has degree 0. And I remember this conversation back when I was a grad student. There was this analysis student. He helped me pass my own analysis qual, so he knew his stuff really well. And just happened at T one day, he comes and he's like, oh, I've got a function on a sphere valued in another sphere, and I'm trying to integrate it, and I do know that it doesn't take on all values. Is there anything you can tell me about the value of the integral? I'm like, it's got to be 0. Because of basic degree theory. So that made me feel pretty good about topology, about my chosen subject, because he's like, really, you just know it's 0 automatically? Yeah. Let's see. Give you some more examples. One of my favorite ones is I can take a genus 3 surface that I make as follows. Oops. I'm going to take 2 tori which are punctured at 2 places, and I can think about them mapping to a genus 2 surface by having the this red here will have preimage there. But if I want, I could actually then connect this to this and that to that. And this would give me, if those connections are made, that's a genus 3 surface. And this projection defines a map from a genus 3 surface folding onto itself to the genus 2 surface. And this is a degree 2 map. I'm pretty sure. I don't think it's 0. I think it's 2. What else? If I have any surface at all, very high genus, I could just take my favorite little ball, and this boundary of that little disk in the surface is going to go to 1 point. Because this is a disk, the interior of that disk would map diffeomorphically onto the rest of a 2 sphere, and everything else out here, all the rest of this surface, is also going to go to this single point at infinity. And if you think about it, then the south pole of this sphere is going to go to this, has just one preimage, the center of the disk. So this is a degree 1 map. But interestingly, this is not an easy exercise. In fact, I don't know of any machinery that would be accessible without a fair amount of study of topology. You could ask, can I go the other way around? Can the sphere map to, I don't know, a torus or a 2-hole torus or any of these? Is there a degree 1 map? Is there a way to sort of take a volume form on the torus and pull back to a volume form on the sphere? And the answer is no, those don't exist. Okay. Great. Right. So that's degree. Degree is sort of taking two manifolds of the same dimension, looking at maps between them and saying, okay, how many times does one cover the other? Make a branch cover is a good examples of degree, but it doesn't have to be, it can be an arbitrary map. Again, it can be a constant map. Constant maps are all degree 0. Any map which isn't surjective is onto the image is degree 0. I want to now go to right from degree to linking number. Okay. So so let's talk about first the volume form on S2. So you have that S2 is, unit vectors. And so the tangent plane is perpendicular to X, Y, Z. So on the circle, that was just minus y x, and this would have to take two things like minus y x 0 and as well as minus z 0 x, for example. Those would be two vectors in the tangent plane at x, y, z. But the point is that if I'm going to project onto that, then in this isomorphism between two forms and vector fields, we're going to, so projection onto this is going to be the sum of projections onto x, y, y, z, and x, z planes. And the weighted by dot products of the normal vectors. And so you get, x, y, z dotted with 0, 0, 1 dx dy for that projection. And then x, y, z dotted with 0, 1, 0 dz dx. And that seems odd, but it's the right-hand rule, x, y right-hand rules up to z. Xz would right-hand rule to negative y. So zx right-hand rules to y. And then finally, we've got x, y, z dotted with 1, 0, 0 dy dz. And so I get z dx dy plus y dz dx, which is the same as minus y dx dz if you insist. And these should be wedge products here, but we often leave those out, plus x dy dz, and that's on the unit sphere. And so, but then if I want this form, which lives on the 2 sphere, to live on all of R3 minus 0, I could perform the same kind of calculations I did at the beginning of this lecture with the pullback from the circle to R2 minus 0. But we can also argue, that is, if this is to scale properly, on R3 minus the origin, so that the integral will always be, well, though I didn't put a 1 over 4 pi. So the integral over any sphere around 0 is going to be 4 pi. Well, if you think about it, if x is scaled by c and y is scaled by c, etc., and then that means that dx is going to go to c dx scaled by c. So this expression is going to scale by c squared. And so I have to then undo that. And by dividing by the scale factor c, if c is how far I am away from the, if c is my distance from the origin, I have to divide by c cubed. So that implies, so the radially symmetric volume form with unit volume on R3 minus the origin is going to be, if I want the unit volume form, I've got to take 1 over 4 pi times this z dx dy plus y dz dx plus x dy dz over x squared plus y squared plus z squared to the 1/2 cubed. All right. So that's the classic thing. All right. I next want to talk about then linking number integrals. So I've got some link. Let's make it a little bit interesting. Well, from at least one perspective, this is interesting. From the integral we're going to write down, maybe this is not so interesting, but take something like this. So I've got two components. Let me label them L1 and L2. These are just closed curves in 3 space. They can't intersect one another. And what I'm going to do is assume that L1 is parameterized by 3 functions. The x coordinate is going to be a and the variable s. So s is going to be some variable on a single circle. So s parameterizes the first circle, and then functions a, b, c parameterize in that circle coordinate, parameterize the first link, and they'll do e, f, g, which are now of the second link component coordinate, parameterize the second one. And what we're going to do is we take this data and we produce a map from S1 cross S1 to R3 minus the origin. And it's just going to take my 2 link components to the vector that measures the difference. And it's going to be non-zero because L1 and L2 themselves don't intersect. So I'm going to just take A of S minus E of T, B of S minus F of T, C of S minus G of T. That's some vector that points from the first link component to the second link component. So some vector like that. If I'm using the S, here's where my S is realized on L1, and here's my T realized on L2. Okay, so let's pull back this standard volume form. Okay, and let's just focus on So I'm going to call this this map gamma for Gauss map. So we're gonna and we're gonna pull back the volume form or the symmetric two form. So we're gonna pull back the symmetric two form on R3 to S1 cross S1 and integrate. This is a homotopy invariant. Under homotopy of gamma. And that is thus isotopy of my original L1 and L2. Okay, so well, we're going to take this formula z dx dy plus y dz dx, etc. Let's just focus on the z dx dy. Let's call this form rho. Okay. So what is the pullback of rho? Once again, you just so in our language, pullback is going to be this gamma that we've defined, and I'm pulling back rho equals, I'm going to get a few different terms, but the z dy dx, let me make this maybe even smaller because we've got the formula for the form up there. So I've got z dy dx. My z is, for this difference, is just going to be, you know, c minus g. My dx is going to be, you know, so d of a minus e, which is going to be, I'll write it a prime ds minus e prime dt. That's what my dx pulls back to. My dy prime, my dy will pull back to b prime ds minus f prime dt. And then I'm going to have two other terms like this. And then all of that is going to be multiplied by, you know, 1 over c minus g squared plus, well, a minus e first, I guess, and b minus f squared c minus g squared to the 3 halves. Okay. But now we can use the rules for dealing with forms that we discussed last time. And notice that ds wedge ds is 0. That's one of the basic rules of forms. And so I get c minus g. I'm going to get a prime f prime, and I'm going to have a minus that ds dt minus e prime b prime dt ds. And if I simplify that, I get c minus g times, well, dt ds is minus ds dt, so I get e prime b prime ds minus a prime f prime ds dt. And I would have two similar terms, and then I would have this 3/2 denominator. And now if instead of ABC we used, and then I also, by the way, have a 1/4 pi. Suppose I use, instead of ABC, I use X, Y, and Z, and maybe X prime, Y prime, Z prime. And also for this derivatives, instead of prime, we'll use very different notation. And well, let me just write it down. You get something like this. The C minus G is just your coordinate Z minus Z prime. This is due to Gauss. Your E prime B prime becomes a dy dz prime. Your minus dz dy prime, and then we don't have any ds or dt because he had a different way of doing this. Not a real, well, different way of doing this, and also a different way of writing this. And then you would have an x minus x prime squared plus y minus y prime squared plus z minus z prime squared to the 3/2. So if you switch from a's, b's, c's, d's, f's to x, y, z, x prime, y prime, z prime, prime is no longer derivative, it's d. We no longer have our differential forms around in the same way. So it's fairly different notation, but it ends up being the same integral. This is the Gauss integral for a linking number. And it's just something he put in a little note to himself. Gauss was studying things like electricity and magnetism. There's in fact a little paper that speculates about how Gauss might have thought of this. It appeared in the Journal of Knot Theory Ramifications. Sorry, I'm not remembering it immediately. But it's a very concrete integral. And what's remarkable about de Rham theory is that you don't have to be Gauss to, quote unquote, come up with it. These standard principles that differential forms can lead to homotopy invariance if you just pull back and integrate. And then the clever thing is to think about a link and make this auxiliary map from, I mean, this is the fun thing to maybe visualize. I wish I were artistically better, but this is some map from a torus to 3 space, and the torus is going to include maybe some number of times. It could really kind of wrap around itself, but the real question is how many times it's enclosing 0, and that's this linking number. And that's what Gauss intuited from, again, almost certainly some sort of physical considerations back in the 1800s. But we can just use the structure of how de Rham theory was developed and say, all right, here's a way to make a homotopy invariant, and it makes a link invariant. And so automatically, we know from our general theory that this integral will not change if I move the 2 components of the link, whereas Gauss didn't prove that directly. And I imagine it would be a challenge to prove directly that if you write this concrete double integral down, you would have to think a lot about why it doesn't change as L1 or L2 and or L2 moves a little bit. Okay. We could also, so I wanted to mention that, actually, maybe I'll leave it for next time when we're talking about the Whitehead integral. It'll be important that we don't have to pull back this gamma. I'll just say it, and this is where we don't have to pull back this particular row via gamma. I could choose, for example, something concentrated, and this, like we've done for the degree theory, and this could lead to accounting formulas for the linking number. So yeah, I think I'll start next lecture with that, some alternate views of linking number, and then finally do the Whitehead theorem. So